Welcome to EDU AMP. Today, what I'd like to do is I'd like to cover the A-level physics syllabus on stationary or standing waves. What you need to know, be able to do, is label nodes and antinodes in a stationary wave and explain what these both are. You can explain how stationary waves is formed, state conditions needed for the formation of stationary wave using a graphical method, and link the distance between nodes to wavelength for a stationary wave, and contrast stationary waves and progressive waves. Now, stationary waves you meet in everyday life, especially if you play a musical instrument like a guitar or a violin, because this is how music is formed. So first of all, what I'd like to do is I'd like to show you how these waves are formed. Now, to do that is I'm going to show you this simulation here. So I want to imagine you've got a string. The string is here, and it's shown basically by these red and blue balls, and these basically representing the particles in a string. Now, it's fixed this end by a clamp, so it can't move at all. And this end, the arrows here, is allowed to vibrate up and down. So if I take that and basically wiggle it up and down, I'm sending a progressive wave all the way along from point here, this side to that side. And like we've done before in progressive waves, these particles can vibrate up and down in a vertical plane, and no time at all can they vibrate at all in the horizontal plane. And because they go up and down all at different time, going up and down like this, you see the progressive wave goes down along here, but when it hits the fixed end, it reflects. Now, the first thing I want you to see is, and it's tricky to see, I hope you can see it, is that when the wave goes down, when it reflects, if it's going up here, can you see when you reach this point and it's reflecting, it reflects coming down. I'll try and send one to pulse it up and comes back again. So in other words, when it reflects, it comes up, and when it reflects here, it moves down. That shows me there's a phase shift at this point here, and the phase shift is actually going to be 180 degrees. That's important to see, because if you add two waves, and we had superposition we talked about last time, if you have two waves that are superposition, and the 180 degrees or pi out of phase, won't the resultant wave be zero? In other words, this point here is always going to have no amplitude whatsoever. Now, the important part to see, if I now started oscillating and I'm now constantly sending waves out here, eventually you've got one wave going this way and one wave going that way. And what it starts to do, it starts producing this standing wave. What I mean by that is, if I keep reflecting here and goes back, what you can see now is a wave that doesn't seem to be moving anywhere, and this is called a standing wave. And a standing wave's caused, and the wave goes down like this, and the wave comes back through here, and they're going to interfere, and you've got superposition. And what starts forming is a standing wave, and you can just about see it here, where you can see waves, and the wave's actually not going anywhere at all, and it's a standing wave. Now, to show it better to you, I'm going to go to this simulation here. Now, on this one, what you've got, here's the red wave, which the wave is coming from the left-hand side to the right-hand side, and it's traveling along like this. What the blue wave is showing you is a wave reflecting on that fixed end in that previous simulation. So if I now take these two waves together and I merge them over each other, this shows me at any time what is going to be the resultant wave. In other words, what I'm doing is adding the amplitude of the red wave and the blue wave together. So if I take this point here, I've got to add this bit going up and that bit going down. If I go over here, I take that wave going up and the amplitude that going down. Now what happens then is you get this black line. This black line is the resultant standing or stationary wave. Now, example, this point here, which is zero amplitude, is going to be that point going up and that point going down. If you add those two together, you get zero. Here, I've got this going up and that going down. The amplitude positive, the blue going up, is bigger than that, therefore it goes up here. Therefore, what I'm going to do is I'm going to take the merge away and put the black line down. And what I'm doing now is showing you the red going from left to right, and the blue going, so left to right, this one going from right to left, and you see the resultant black wave happening here. And this is the standing wave I was trying to show you in a previous simulation. Now it's important to see this part just here always has no amplitude whatsoever. This is called a node. This point here is going 0 maximum positive, 0 maximum negative. This is called an antinode, and you've got an antinode here, an antinode here, and an antinode there, and an antinode there. Here, there, these points are always going to be your nodes. And this is what a standing wave is. So a standing wave is made by one wave going this way and one wave going back. And when you've got a guitar and you plot the string, basically you produce this standing wave, and this is how music is formed. Now what they can ask you about in examination questions is these two waves, either red and blue, are progressive waves. This standing wave does not transfer energy. What I mean by that is if this sends energy going across this way and that gets energy going back that way, what it is, it's storing energy. In other words, no energy is actually transferred along the string here. Now, to go back where I was before, now this shows you how stationary wave is formed. Now, what you need to do in examination questions is you need to basically show how a wave changes with time. So if you've got your standing wave, here is the resulting standing wave, and it's made by one wave going, which is a dotted line going to the left and then reflecting going back. That's how it looks like at 0 time. If you go then whole half time period going through, are we halfway through a cycle, won't it then be going down here and going back up again? In other words, it started with the left-hand side being a antinode here, going down an antinode, going through a whole half cycle later, it will then look like that. And they do ask you how the standing waves change in time. Now, to work out how the wave changes, what you do then is you go to half it to quarter of a time period. Would it make sense a quarter of a time period was where you've got no disturbance whatsoever? Then, if you go to an eighth, wouldn't this point going up and going down, that would be halfway up, which is going to be this point here, is made by this wave going along this way here. It reflects and that wave comes back, and all you're doing is adding the amplitude of the dotted lines together, whereas those two together make that. This goes up positive here and goes down here, therefore it's going to be 0. If you then take halfway between the quarter and the half, i.e. got 3/8, well, you now have the wave going partly going down, where these two dotted lines, that and that going down, gives you this. In other words, what it's showing graphically in time, how they're changing. And to go back to my simulation, it shows you how this goes up and down with time, where this is 0, quarter, half a time period, 3/4, a full time period, going up and down like that. Okay, so these are the very important points they can ask you about. And if they get exam question, to basically ask you to explain the features of stationary waves, this is what they ask you. First question here, it says simply ask is what is the points of no displacement called, and these are simply going to be called nodes. What are the points of maximum displacement called, and these are called antinodes. In terms of wavelength, what is the distance between adjacent nodes? What that means here, going back to my simulation, if you've got a node here, so antinode here, and an antinode just there, what you need to realize is going across here, going back to where I was, is a case this is going to be half, right here, it's going to be half the wavelength. And exactly the same in terms of wavelength, what's the distance between antinodes? Again, that is going to be a half a wavelength, because if you have the wave going up and down like this here, this shows you, and we saw we normally dot it like this, showing it change with time. The distance between these two here, that's going to be half a wavelength. the node here and the node here, again, that distance is going to be a half a wavelength across. In the region between successive nodes, comment on the phase, and that should be a D there. Comment on the phase and amplitude of the particles. Therefore, what we're doing here now is we're taking this one here. I'm trying to hold my black pen here, which refuses to work. Go into that black one there and that one black there. These particles here, between successive nodes, comment on the phase and amplitude of the particles. All these vibrate up and down in the same phase. Okay, but it was important to see, and I'm doing now in black, showing the amplitude, is the amplitude of all these. It varies, where this has got no amplitude, that's got a maximum amplitude halfway along here, and this antinode, and again it starts going down here. So they all have here are going to have a different amplitude. Okay, and these are sort of things they can ask you about, is basic features about a stationary wave. And then finally, comment on the phase relationship with adjacent loops. So we're looking here at this loop here and that loop here. They're simply going to be 180 degrees or pi out of phase. What I mean by that is, if that one's going to be going down here at a as a snapshot, this one is going to be here. Therefore, it goes top to bottom. They're always going to be the opposite end of the amplitude. This has gone down here and that has gone up. Therefore, we say they're going to be pi 180 degrees out of phase. And that's all the features of a stationary wave. Okay, so to recap what I have just been through, is now we should be able to label nodes and antinodes of a stationary wave. We should explain how they're formed. And now we have linked the distance between nodes with wavelength of a stationary wave. And the last thing we're going to do now is compare contrast stationary waves and progressive waves. And this little bit comes here. So if you have got your stationary waves, and here you've got your progressive waves, what they can do is ask you about the features of these. Now, basically, all you've got here is you've got, in stationary waves, all the particles go up and down. Well, all them going to have is going to have the same frequency. And in the progressive wave, again, all the particles must vibrate up and down at the same frequency. And finally, secondly, going through the amplitude in a stationary wave is that the particles are going to have different amplitudes, because you've got a maximum in the antinode. Important to note is the fact that if you've got a node, you've got no amplitude whatsoever. And the progressive wave, aren't they all going to have the same amplitude, because they go up and down, but they all can have the same amplitude, or maximum amplitude, as the wave goes along. And the phase difference between particles, this is where we use that equation, is you can find the phase difference. So you had a progressive wave going across like this. Before we talked about here, where you had naught going through all the way through here, there's going to be 2 pi. You can find the phase difference all the way through for the different particles away by using that formula. In the case of here, between your stationary wave, which is going up and down like this, and here's going to be your dotted line going like that. What they normally do, there's some of the books call this, they call it a m pi. What I mean by that is, if you've got the particles in this loop going over here, and I'll get a different colour pen to show it to you. If I've got this loop over here compared to that loop over there, I said before they're going to be pi out of phase. Therefore, if I go across to this one compared to here to that one, then it would be 2 pi, well, actually going to be in phase. Therefore, what it does, in these two, you've got m equals 1, i.e. pi, and from there to there, you've got 2 pi, because then you've got here 306 degrees or pi or 0 phase difference. You can use that formula, but I think it's easier to see it in your head. the fact that you're going to have a phase difference between adjacent loops going here. Okay, so I've now just finished off that very last learning outcome, compare contrast stationary waves with progressive waves. Hope you enjoy the video.